All right, welcome back to our conversation of exponential growth. So far we've been looking at equations of the form y equals y sub naught e to the kt. K is a growth or a decay constant. Um, we've looked specifically at e because it naturally falls out of the derivation of the equation where we did separable differential equation. Well, what we want to look at today is what if E is not an easy one to use? What if E is not the obvious one? Can we actually make it simpler by choosing something other than E? And what we're going to do is we're going to write the equation y equals y sub naught b to the ht. Notice that h is not equal to k. It is something different, and we'll look at that a little bit later, but we can actually show that h is just equal to the decay constant divided by natural log of b. We're not going to talk about that specifically right now. And also, b can be any number greater than 0 except 1. Technically, it can be equal to 1, but then you just have a constant value, and that's boring. So it won't be equal to 1. So let's look at a population that doubles every 5 years. Well, if we are doubling every 5 years, it makes sense to me that our multiplier would be 2. Now, since it doubles every 5 years, we also know that the population will be twice the original when t is equal to 5. So let's do a little bit of simplification. We divide both sides by y sub naught. 2 is equal to 2 to the power of h times 5. Clearly, h times 5 must be 1, which means that h is equal to 1/5. And therefore, the equation for a population that doubles every 5 years is y is equal to y sub naught 2 to the power of t over 5. So the next question might be, well, if we look at this equation, what about the same population? When will it have tripled? And so what we now have is that 3 times the original population is equal to y sub naught 2 to the t over 5. Y sub naughts cancel out. And we're going to take the natural log of both sides. So natural log of 3 equals t over 5 times the natural log of 2. Hopefully at this point you're okay with the log rules that allow me to do that. We'll divide by natural log of 2, multiply by 5, and we discover that our population will triple in this many years, which is about 7.9 years. Now, why would I do this instead of just making my base 3? Well, the problem with making base 3 is that I don't have any data. I don't have any data that tells me when it gets to a certain place. So what I'm actually doing is I'm just using the it doubles every 5 years to now calculate some triples. All right. But what I do notice from this, and this is something that maybe we can take away, is that our value of h was 1 over the time, and it's 1 over the time required to double in this case. So if I'm going to use a double, which means that b equals 2, then h is equal to 1 over the time it took to double. All right, very quickly, one more. Oh, switch back to black. Very quickly, one more. Population triples every 10. Now, years, because I am tripling in a certain amount of time, I can write my equation as triples every 10. Becomes really easy to write that equation. I don't even really have to do a whole lot of thinking about it. My equation is 3 because it triples and t over 10 because that's how long it takes to triple. So generally, y equals y sub naught base to the power of t over time to base. There's my general equation, and now I can use that moving forward. So now let's take this equation and very quickly ask ourselves, well, when will that population double? And I know that I'm looking for 2 y naught times y naught 3 to the h over 10. The y naughts cancel, taking the natural log of both sides. And I see that h is equal to 10 times the natural log of 2 over the natural log of 3. You may be noticing, excuse me, I wrote h. Of course, I meant t in all those places because I was in a hurry. That's what happens when you're in a hurry. You make mistakes that you wouldn't have made otherwise. And that's approximately 6.3 years. You may be starting to notice a little bit of a pattern in where numbers go in here. Honestly, I feel like it's actually easier to solve it than it is to start finding those patterns, but I bet you could generalize this kind of problem. So let's do one more. I don't want this to go too much longer, but we'll do one more example, which is we have an isotope of sodium, Na24. It has a half-life of 15 hours. And we've done half-life problems using a base of E, but why not do a half-life problem with a base of 1/2? Because we know that that'll just be T over the time it takes for half of the substance to decay. So question then would be, well, when do we have 10% left? And we would be able to just say, well, when we have 0.1, the original amount, that's equal to the original amount times half to the T over 15. Reduce those. Natural log of 0.1 is equal to T over 15 natural log of 1/2. The time to 10% left is 15 natural log of 0.1 over natural log of 1/2. And plugging that into my calculator, I get approximately 50 hours. If it has a half-life of 15 hours, it will take about 50 hours for 90% of it to decay away. And I had said one last example, but now this will be the actual one last example, which is how do I choose a base? Let's talk about a bald-faced hornet's hive. And I have some data. I know that on May 1st, there are 10 bald-faced hornets in a hive. After 30 days, there are 50 bald-faced hornets in the hive. I'm going to say that this is going to be a base of 5. It's getting 5 times as big. I know how long it takes, which means I can dive right in and write an equation, 5 to the T over 30. In days, when will there be 100 hornets in the hive? H in the H. And 100 is 10 times the original amount. Or I could just type in 100 equals 10 because it's y sub naught. 5 to the T over 30. And what I see is that the time is 30 natural log of 10 over natural log of 5, which is approximately 43 days. There will be 100 hornets in that hive. All right. Thanks for your patience. My students, go ahead and do exercise 23 in the book. And we'll be back with some examples on carbon-14 dating and something called Newton's law of cooling. Thanks for watching.